Swayam Prabha. Digital India. Educated India.
When you get into networks are a very how would I say, it's a very active area of utilization and research, both computer science, mathematics, and in many areas. So something like a graph theory or network analysis is a whole domain on its own, and the fact that we choose to use networks to do our time management or time planning is itself quite an innovation. Okay, so I'm got the slide here where I'm showing you basically, I think when we talk about network, all of us know what a network means. Okay, and I mean everyday context, we talk about road networks, pipe networks, cable networks, internet is a network. There are so many kinds of networks, and when you start representing the network in the form I've shown here, which a network consists of a node and a link or an arrow. Okay, so you have here you have a single directional network where the arrow goes only from I to j, or you can have bidirectional. Okay, you can have I to j, j to I. Now something like a road can be represented, this might be like a one-way street, this is a two-way street. Okay, now if you look, like I said, it's in many domains. So you can have roads. For example, you can see this image here, where you can see nodes and links or nodes and arrows. Okay, so this is a network. Now you can imagine, so what are the nodes consist of in a road? Intersections. Okay, links are the roads themselves. Same thing in a pipeline, same thing in a truss or in a frame. Okay, you talked about telephone, you can have telephone networks, internet, all of these are networks. Now you have social network. Okay, so is social network a physical network? Is it physical really? It's not really a physical, it's basically, see what you see here, basically they are saying so many people are linked to so many, who's on your network. So in a way it's physical, but basically all you are saying is you are linked socially to somebody else, and the algorithms and techniques of network analysis can be applied to social networks also. So networks and graphs are a huge domain which is very rich mathematically. We are only touching the tip of the iceberg in its utility for project time management. Okay, so this is the kind of what I would call it, probably when you look at a project, do you see a network in a project? Is it as natural as a road network? Certainly not, it's not. It's not as intuitive as a road network. So if you take a network from a project perspective, it's more abstract than a road. We have to start representing the road as a network. Is we can see the junctions, we can see the links, we represent it as a network. Representing a project as a network is not so intuitive. Okay, so we really have to applaud the people who thought of representing the project as a network. It's a higher level of abstraction, and this was something that came out in the 50s, and it was an effort by DuPont, Remington Rand, and UNIVAC. Okay, so DuPont needed construction and maintenance of its works and things like that. Remington Rand was a management consulting group at that stage, and UNIVAC was a computer firm, and they got together and developed the CPM scheduling method. Okay, and network planning, and at that time OR and graph theory and all were in the developmental stages, and the team that got together really were very innovative to put this together and use it in terms for construction planning, and they developed the critical path method. There is quite a bit of history to it, and I'll give you some references at the end where you can read as to how the terminology we use today is not necessarily the terminology that was originally used, but the techniques are relatively the same. There is also a lot of debate on whether the original technique is actually more authentic for construction planning than some of the techniques we use today, but some of this we will take on later in the class. Okay, we will go through the basics today. Now when you take CPM, the nice thing is that when you compare it with a bar chart, one of the limitations you remember was that we could not represent relationships. Okay, so here you can represent relationship between activities. Number 2 is there is a certain mathematical background to the way CPM is done. The bar chart, did we have any analysis from a bar chart? No, it was a good communication tool, okay, but more than that it didn't give us any more results. We could, once we applied our mind to the project and expressed it in the form of a bar chart, it served as a good communication tool. You could update the bar chart, you could use it in many ways, but it was mostly a visual communication tool. Okay, visual communication and representation. A network offers more than that, and we will see some of that. One of the real limitations of the network is that it requires training to interpret. You could see something like a bar chart, we can discuss it for half an hour or even less and someone can use it straight away. But when it comes to CPM, you really need quite a few hours of introduction, and even then a lot of practice to be able to use it effectively on a project. Now when we look at, so the first thing, when you take a network and you look at a project in terms of a network, what you have to understand is how do we actually represent a project as a network. Okay, so we got clues so far. We are going to break a project into activities, we are taking those activities, we are sequencing the activities, and so on. So we certainly understand activity is one part of this network representation, and the other part is the precedence relationship, the relationship between activities. So in the original representation, which is called activity on arrow, okay, AOA, the nodes represented the start and the end of the activity, and the arrow represented the activity itself, okay. Now we'll do a small exercise on this problem for you to understand, or for you to be able to see why people like Fondal came out with activity on node. Okay, so when we take activity on node, you will find that the activities are represented by nodes and the relationships are represented by arrows. And then you have the precedence diagramming method, which was IBM's extension for activity on node, and this is even more offers more sophisticated features than activity on node. So what we will cover today is a little bit of activity on arrow, more on activity on node. Precedence diagramming gets its own 2 sessions later on in the course. Okay, so like we talked, activity on arrow, you have an there's an event I and event j. The event is the start of the activity and the end of the activity. Activity is represented by the arrow. Okay, now there are some conditions one should follow. We should have, all events should have unique numbers in this representation. Activities must have unique ij combination. I cannot have 2 activities represented in this form. There is no question of having closed loops or dangling activities. So all activities have to end with a node. Okay, now if we take the inputs for a network, what you have shown you here is a set of activities and a set of predecessors, right. So when you take activity A, it means that only after the project starts we should be able to start. Once you start, yes, then only activity A starts. To do activity D, activity B should finish. To do activity E, activity A should finish. So this is called the relationship. So for example, to start activity I, activity F and G should finish. Okay, so now you have seen the rule for making activity on arrow diagrams. Do you think you can try to represent this logic through activity on arrow? Can you try it? Remember, the arrow is the activity. Done? We'll just take a look at the network, and you can compare what you have had with what is here. So this is, you can see there's a start, you have activity A, B, C succeeding the start, you can see activity D is after B, E, F, okay. So E is after A, F is also after A, F is this, okay, and activity G is after C. Now activity H requires A and C as predecessors, right. So right now if I start activity H out of here, what happens? Out of 18 to 26 if I join, no, A is not included, okay. If I join from, so what we do is what AOA requires is the concept of dummy activities. So we have two dummy activities which enables us to create this node and then link 20 to 26 and make it H, okay. So it is not just the inclusion of dummy, you will find that as even with representing E you might have had some difficulty, okay. You would have had you would have started off with one loop and found, oh, there is redundant activities coming in and things like that, okay. So then you can follow the rest, you will see J has got D and E as predecessors, K as J, H and I as predecessors. Now this you experience a little bit of the difficulty of what AOA causes, which is this inclusion of dummy activities, and when activities are on arrow almost always it is very difficult to draw the network logic cleanly the first time. You will have to keep repeating because only the topology of the network will govern the logic, and only as you do it in a couple of times you can optimize it to the minimum number of nodes and arrows, okay. So this was a challenge in the past, and in the earlier programs which had activity on arrow would have a round of optimizing the network itself, okay. So that was one of the challenges. So here we have what we call the dummy activity to capture the precedence logic. Now so a lot of activity on arrow, a lot of the activities were also dummies, okay. No duration, only requirement to catch logic. Now let us move on to activity on node. So activity on node was proposed as a good way to do hand calculations for CPM. This was what Fondal had written in his paper. It was some of the work he did for the US Navy, and he said, look, you can now use a technique which use activity on node, and you can actually it's intuitive, so you can do hand calculations with it. And activity on arrow really needed for large networks needed a computer program to do your network representation and calculations, okay. So here you will find you have to tell me, okay. So basically what you have here is you have the activity in the node, the relationships are represented by arrows, okay. So if an arrow goes from a node to another node, it means there is a succeeding activity, otherwise it is a preceding activity, okay. Now here I have made some statements, so no dummy activities are required, it is easier to interpret, and most software tools use AON than PDM. The last statement is true, and that is one reason for the real usage of AON growing a lot, but I want you to see if these two are something which you can validate, if especially the logic is more naturally represented, okay. So let us take the same problem and you try to do an AON now. Done? Much simpler, okay. The logic flows and you are able to go through the whole process without you might get a few arrows crossing which sometimes cannot be avoided, but basically you can find here that your activities are on the nodes, arrows represent relationships. As you go through the network you start drawing your arrows, putting your remaining nodes, and it flows through. Now this representation and this representation contain exactly the same information, same topology, okay. From a human perspective this is much easier to interpret, and we will continue with this for the hand analysis, okay. When we go to precedence diagramming method you will find that it becomes as tricky as this in some ways. So and the reason for PDM being tricky is this, that so far we have been talking in AON and AOA we have only talked about finish start relationships, that an activity should finish before the next starts, that is the only relationship we can represent. When we go to a precedence diagramming method, the key difference is there are other relationships, So you can see there is something like a start relationship which says that, and here I have included a lag also which says B can start only 4 days after A starts, okay, or a finish relationships. You can have the conventional finish start relationship and a very kind of not so much used start to finish relationship. Okay, we will take more of this during the lecture on PDM. We have few sessions on PDM, we will take more of it then. And a PDM network will look something like this, where you have the various relationships which are shown, and this can also get complicated to do by hand because of the different types of relationships involved. But again, we will take this up later in the PDM lecture. Now, we talked about network representation so far, and one thing which we have to recognize is so right now I have actually given you the relationships. Establishing those relationships can be tricky, and we will take more of those sequencing, as we call it, when we actually take up some cases. But when we look at the analysis of a network, you will find we talked about activities, we have to find the relationship between the activities, we talked about durations, we will talk about resources later, we talked about resources with respect to duration, but we have to have resource management, which is a separate area on its own, and we will take this up later in the course. But given relationships and durations, these are the outputs we get from network analysis, what we call early start, early finish, late start, late finish, the project duration, the critical path or critical activities. We have a series of floats or slacks which we get, which is total float, free float, interfering float and independent float. Okay, so what we have to do, or what we are going to cover in network analysis, is to kind of illustrate what each of these mean and how they are calculated. Okay, so in this session we will primarily talk about the times, the early start, the finish and the project duration and the critical path. Okay, so we will take a little bit on the definitions. You can see it here. The early start is the earliest day on which an activity can start. The early finish is the earliest day on which an activity can finish. Late start is latest day an activity can start without delaying the project duration. Okay, we will illustrate this, it will become clearer. Late finish is the latest day an activity can finish without delaying the project. Project duration is minimum time required to complete the project, and the critical path is the activities on the longest path in the network. Okay, we will kind of illustrate these, calculate these quantities through an illustration, and this is the illustration which I would like to use first. It is a very simple network. Okay, you can see it has just got 4 activities, A, B, C, D, and you have the durations given there, and you have the predecessor relationships. I think all of you will be able to draw the network pretty easily. Okay, so let me take this as, so A has, so I am going to do activity on node representation. So A has no predecessor, I have B, and D. So this gets a network through. So you can see D has B and C as a predecessor. Okay, now you have durations, and in my notation I like to put the duration on top of the activity. So you have a duration of 5, B has a duration of 4, C has a duration of 6, and D has a duration of 3. Okay, so I like to keep the duration, and as far as we are concerned, the duration is constant, it is fixed, we are not changing the duration for this analysis. I like to make a notation in this form, which makes hand calculation easier to interpret. And what we are going to do is now we are going to calculate. So if this takes care of the first part, which we have represented the activity on node network. Okay, now we are going to the second part, which is called the forward path. Okay, we take the network from left to right, and we use a certain terminology for time. We say that this starts on 0, which is actually the beginning of the first day. Okay, we put 0, it's going to take 5 days. We put 5 here, which is actually the end of the 5th day, okay, because that's a 5-day duration. So A starts beginning of the first day, which is 0, end of the 5th day. Now we have 2 activities, so when can B start? Yeah, so we are putting 5, which is actually the beginning of 6th day, okay. So we are putting 5 and 5. We go to 9, okay, we go to 11. Okay, so now between 9 and 11, when can D start? 11. So obviously it has to wait for B will finish by 9, it has to wait for C to finish because it's a predecessor, and only then it can start, and D can finish on 14. Okay, so what we have calculated here is the early start, early finish of the whole all the activities in the network, and ultimately landed up with the project duration. So this network will take, this project will take 14 days to complete, and we found early start and early finish through the forward pass. Now what we do is we actually have to find out the late finish and late start. So remember, what was the late finish? Latest an activity can finish without delaying the project duration project. Okay, so our project now is fixed at 14, we cannot change that. Okay, so D can be changed, it's 14, and when should D start to finish by 14? 11. It cannot. So this becomes 14 minus 3, that's 11. How late? So we are talking about late. Now how late can B finish? 11. So even if B finishes by 11, we are okay, project is okay. C 11. Okay, now C has to start, latest it can start is by 5. Okay, and what about B? 7. Yes, so 11, it is 4 days, the 4 is a constant, so it comes to 7. B has the latest it can start. What happens if B starts on the 8th day? Yeah, 8 days, this goes to 12, which means D can only start on 12 and project goes to 15. Okay, so this is 7. Now I come to A. I have 5. What is the latest A can finish? 5. If I finish after 5, what happens? C gets delayed. Okay, and 0. So this is the backward pass. So we did the forward pass to find early start, early finish, the backward pass to find the late times. Now can you observe, so we have 2 paths, one going ABD, the other going ACD, and you can see that, is there any difference between any of the activities you can see in terms of time, in terms of the relation? So here you have 0 5 0 5 5 11 5 11 11 14 11 14 5 9 7 11. Okay, here the late times are different, which means there is something different about B compared to C, and that is slack offload. We will take that up later, but you can see that there is something different. Now what we talk is, if I delay B by 1 day, what happens? It's okay as far as the project is concerned. If I delay C by 1 day, project gets delayed. If I delay A by 1 day, it gets delayed. Okay, so these activities are critical. So activity A, C and D are critical, and really the critical path doesn't mean as much as identifying the activities that are critical. So if we want to draw a path, we would say the critical path goes through this. Okay, so this was a simple example which illustrates basically how the network analysis is done, and we have calculated all the parameters which we talked about: the early start, early finish, late start, late finish, project duration and identified critical activities. Now here we have identified critical activities more because it is a simple network. The actual algorithm to identify critical certainly depends on the float, and when we cover float in more detail we will come to that. Okay. Now the same network I can show it you in a brief animation. It is exactly what we did by hand. Okay, and these are the times. Now how would you like to see? Do you like to see the results like this, or do you like to see it in some other form? What would be the best way to express these results?